Hi everyone. So in today's video, we're going to continue to talk about related rates like we did in yesterday's video. So yesterday's video, we did some fairly straightforward examples where basically the main challenge of the questions from yesterday's video was the calculus part, right? The figuring out how do you take the derivatives of things that look like this, kind of getting down this whole procedure of using implicit differentiation in this new context. So in today's examples, the challenge is going to more come from the actual questions being asked. So today the problems we're going to work on are going to be word problems where there's just a little bit more to kind of figure out. And so for that reason, it's going to be really important that we follow the steps that I lined out yesterday. So I want to write those down again. And we're going to write them in a slightly different order than we did yesterday. It doesn't really make a difference, but I think the ordering I'm going to write down now is maybe a little bit better for some of the questions we're doing today. So first step is going to be to draw a diagram. So we saw that yesterday we didn't really do that for any of the questions, and that's because all of those questions, they kind of told you like what shape it was that you were dealing with, right? It was like, a circle is expanding or a triangle is expanding or something like that. And in these questions, you have to kind of figure out yourself what shape are they talking about here. And the best way to do that is to draw a picture. So the second step is going to be to assign variables to the quantities that are changing. So that are changing part, that's going to become more important today because today we'll have, for example, one question will have to do with a ladder that's sliding down a wall. And the ladder doesn't change length, right? It's just one length the whole time. So for example, in that question, we're not going to give a variable to the length of the ladder because it's not a quantity that's changing. So we'll want to really keep track of that. Next step, so this is what I'm switching the order of. So next step we're going to do is we're going to express the given and the desired information in terms of derivatives. So desired information meaning like what are we actually trying to solve for? And so when we say in terms of derivatives, that's like things like dv dt or dA dt or dr dt. And that step is going to be really, really important to really keep track of like being able to go from the word problem to the calculus part. You really need that step of being able to understand what the derivatives are in this question. So next step we'll do is we will write an equation relating the quantities from step 2. So whatever those quantities are that are changing, write down an equation that gives you a relationship between them. And then the next step, once you have that equation in hand, then you can differentiate that equation. And when we say differentiate, we mean we're going to have to do implicit differentiation. So differentiate the equation that you made in the previous step with respect to t. And yesterday we saw how that works. Basically, you're doing implicit differentiation, and every time you take the derivative of a variable, you're always multiplying by the derivative like dv dt or dA dt or whatever that variable is. And then the last step is just to plug in the given information and solve for whatever you're trying to find. Okay, so let's get straight into examples. So I decided to pre-type up the questions here because otherwise it would take a little bit long to write them out. Okay, so this question says 2 cars start driving from the same point. One car drives south at 60 miles per hour and the other car drives west at 25 miles per hour. At what rate is the distance between the cars increasing 2 hours later? So in these types of questions, there's a lot of information given. And I find that a lot of students find these problems hard. And I think the reason that a lot of people find them hard is that you get kind of overwhelmed by all the information and you don't know what to do first. And that's why we made this list, right? If you follow this list of steps, then you should kind of do things in the right order. So at least, especially when you're first learning them, I would really, really recommend following these actual steps and not skipping any steps. So that's what we'll do as we solve this together. So the first part, the first step we want to do is we want to draw a diagram. So let's do that. So one thing that's important to understand when you go and draw these diagrams is that the diagram is kind of like a snapshot in time, right? Because in this situation that we have here, the cars are both moving. And it's going to be the same deal with the other questions we work on. It's a moving situation. And so we're just kind of drawing one snapshot. Okay, so it says that the cars start driving from the same point. So I'm just going to put a point here. And one of the cars is driving south. So let's just say a certain amount of time has passed and that first car is now down here. Nice purple car. And then the other car is driving west, and notice it's going slower. It's going 25 miles per hour, so I'll make it a little bit less far. And maybe let's have this one be a blue car. And if you look at what the question is asking, it's asking about at what rate is the distance between the cars increasing. So that means that we're not just interested in the lengths of the line segments that we just drew, but we also are going to be interested in this distance here. Because if we're talking about the distance between the two cars, that means like the direct distance that we would get by measuring diagonally. So this is basically our picture. And if you want, you can add in details of like, okay, this car's driving this way, this car's driving this way. I've found a lot of people, when you draw your diagrams, will start putting all the information in, like you'll start writing something about 25 miles per hour and 60 miles per hour. I think that might kind of overwhelm you. So I would actually not worry about putting any of the rates into your diagram. Just draw a picture, and then in the next step, we'll declare our variables, and then the next step, we'll deal with the derivatives. I think it will just get overwhelming if you try to put every piece of information that's given in the picture all at once. Because I think the most important thing here is to keep track of what is a quantity in the question and what is a rate of change. And when you kind of put everything on the picture at once, you're kind of blurring that distinction between quantities and rates of change. Okay, so the next step is going to be to decide what are the things that are changing in this picture and to give them variables. So first thing we can say is changing is the distance from the starting point to each of the cars, right? So for example, we could call this distance A and this distance B. So those distances are both changing. So A is going to be the distance from the starting point to the, I guess, westbound car. And then B is going to be the distance from the starting point to the southbound car. And I know it might seem like a little excessive to actually write all this out in words, but again, I think that when students are struggling with these questions, it's because you're not really understanding what your different quantities are in your question and what your rates of change are. And I think the more explicit you can be, the more you can actually write down literally in a sentence what it is that you're describing, the better luck you'll have on the question. So the last quantity that is changing here is the distance, the diagonal distance between the two cars. So we can just say distance between the two cars. Okay, so those are our variables. So next step we want to do is we want to go look in the question for information about the rates of change of our quantities. So the first thing that we see is that one car is driving south at 60 miles an hour. So that's the one that we drew in purple. So how can we express that as a derivative? Well, if this car is driving south at 60 miles per hour, that means that this distance is changing at 60 miles per hour, right? Like that's what speed is measuring. Speed is measuring the rate of change of the distance. And so that tells us that dB dt is equal to 60. Maybe I'll do that in purple too. 60 miles per hour. And then the other car is driving west at 25 miles per hour. So similarly, the rate of change of of car A, or of the distance that car A has traveled, is equal to 25 miles per hour. And then what are we looking for here? Well, we're looking for what is the rate of change of the distance between the cars, and so that's c. And so what we're trying to find in this question is dc dt. All right, so that is taking care of all the kind of laying out of the information in the question. So the next thing we want to answer is, we want to write down an equation that relates A, B, and C, because those are the quantities in our question. And so what equation do we have that relates A, B, and C? Well, the Pythagorean theorem, right? Because it's a right triangle. So we can say that A squared plus B squared is equal to C squared. Okay, so next part is to now take the derivative of our equation. So we're going to take the derivative on both sides of this equation, and we'll see if I keep it up with the color or not. It makes me a little slow at writing. So on the left-hand side, we're taking that derivative, and then on the right-hand side, we're also taking the derivative. Okay, so how does this work? Well, when we're taking the derivatives here, we're always kind of doing first the outside part of the derivative. So in these cases, so for example, with a squared, that's going to be 2a, right? Because we're using the power rule. And then we have to multiply by the inside derivative, which is going to be dA dt. So we're going to get, for the first one, 2a times dA dt. And then for the second part, we're going to get 2 times b times dB dt. And then on the right-hand side, similarly, we will get 2 times c times dC dt. Okay, so last step is to plug in what it is that we know and solve for what it is that we don't know. So there's going to be kind of an extra step in this, which is that we have to look at basically like what information do we have and what are we solving for and what do we still need in order to make our equation solvable. So what I mean by that is, so we know what dB dt is, right? So we're going to be able to plug something in for dB dt. We know what dA dt is, so we can plug something in here. We know that we're trying to solve for dC dt, so that's fine that that stays there. But that means that we need to figure out what A, B, and C are, because otherwise we wouldn't be able to actually solve for dC dt. So we need to find some numbers to plug in for A, B, and C. So when we're plugging in these numbers, basically we're trying to figure out what are A, B, and C at the very moment that this question is being asked about. So if we go back to the question, it says, at what rate is the distance between the cars increasing 2 hours later? So that's what tells us, that's basically the key for how we're going to be able to figure out what A, B, and C are, is we know that they've been driving for 2 hours, we know how fast these cars are driving, and so we can use that to figure out at the moment that this question is being asked what those distances actually are. So after 2 hours, we can say that A is going to be equal to, so car A, oops, sorry, my screen sometimes gets stuck when I'm trying to scroll. Car A was driving 25 miles per hour. So after 2 hours, A is going to be equal to 25 miles per hour times 2 hours. So it's going to be equal to 50 miles. So after 2 hours, car A has gone 50 miles. Car B is going 60 miles per hour. So car B will have traveled 120 miles per hour. So how can we find C? So C is the distance between the two cars, right? It's the hypotenuse of this right triangle. And how can we find that? Well, we can just use the Pythagorean theorem. I don't know why I just erased that. So we can use the Pythagorean theorem with the lengths that we just found for A and B and solve for C. So we know that C squared is equal to 50 squared, that's A squared, plus 120 squared. And I'm not going to do all the math out here, but if you use the Pythagorean theorem and solve it, you should end up with C is equal to 130 miles. And this is actually a special kind of right triangle. So you might have heard of like 3, 4, 5 right triangles. So this is a 5, 12, 13. So there are certain proportions of sides in a right triangle where if you kind of know these relationships, you don't actually have to use the Pythagorean theorem. But if you use the Pythagorean theorem, you'll get the right thing. Okay, so now we can go into our equation that we have written above and just plug in some numbers. So now we have 2 times, so A was equal to 50. We just figured that out. And then we're going to multiply that with the rate of change of A, which was 25. And then we have 2 times, so B we just figured out is 120. That's the distance that that car is after 2 hours. And then we also want to multiply by the rate of change of B, which is 60. And then the last step is, or the last part, sorry, this shouldn't be a plus, it should be an equal sign, is going to be 2 times 130. And then dc dt is what we're solving for, so we just leave that as it is. So if you add all these numbers together, so we're going to get over here 2,500 plus, then we get 14,400 is equal to 260 times dc dt. And so if you solve this, you end up getting 65 is equal to dc dt. So what does this tell us? Let's try to translate this back into English. This tells us that the distance between the cars is increasing at a rate of 65 miles per hour. That's what we just figured out. All right, so let's try another one. So this one says a 10-foot ladder rests against a wall. The ladder is sliding down the wall so that the bottom of the ladder is moving away from the wall at a rate of 2 feet per minute. At what rate is the angle between the ladder and the wall increasing when the bottom of the ladder is 5 feet from the wall? So again, a lot of information contained in this sentence or a few sentences. So we really want to take it step by step and really break it down and do each of these steps separately. So our first step is going to be to draw a picture. So in our picture, we have a wall, we have the ground, and then we have a ladder. So let's draw in a ladder leaning against the wall. And so we know that the ladder is 10 feet long. And then that's basically all we know for now. So again, like don't go in and try to write some stuff like, so for example, if you were to go in and say 5 feet here, that would not be a good choice because this distance here is changing, right? When you see this word when, that means that is something you're going to plug in at the very end. So we want our picture just to be a general snapshot. We don't want it to be specific to any one moment. So why did I put in the 10 feet? Well, that's because the ladder is always 10 feet, but it would be a mistake to put in 5 feet right now because that's only kind of at one specific moment. And so that's something we won't deal with until the very last step of this whole process. And so really the only thing that we know for sure in this picture is that the ladder is 10 feet long and that the ladder is leaning against the wall. So in this next step, now we can start to think about, okay, what are the things that are changing in this picture that are going to be relevant? So the ladder is sliding down the wall and it says that the bottom of the ladder is moving away from the wall and we don't need to worry about the rate just yet. So that tells us that the distance here, and maybe let's call that A, that distance is changing, right? Because the bottom of the ladder, it said, is moving away from the wall and they give us a rate. So one of our variables can be A, which is going to represent the distance from the bottom of the ladder to the wall. So what else is changing in this question? Well, one thing that is changing, but that isn't really going to come up is this distance here, right? So if the ladder is sliding down the wall, then, so picture what it looks like when a ladder is sliding down a wall, right? So if it starts the way we have it in our picture now, at some point later, maybe it looks more like this, right? So like as the ladder slides down the wall, this distance here is changing, right? It became shorter here, but we're not actually really dealing with that part in our problem because it never says anything about the distance from the top of the ladder to the floor. If you read through, it never says anything about that. What it does say is the angle, right? It says the angle between the ladder and the wall. So we do want to think about this angle. And again, if you look at these kind of two different snapshots, what's the difference? Well, in this second snapshot, the ladder is still 10 feet, but this angle is bigger, right? And then this distance is also bigger. So you don't have to draw two pictures like this, but if it helps you kind of understand how the situation is changing, then great, then you can do that. But stay general, don't think about like any one specific moment in time. It's just sort of a general sketch. So usually we like to call angles something like theta. So let's use theta here. So theta is going to be the angle between the top of the ladder and the wall. And that's really all we'll need in this question. So, if you wanted to, you could assign a variable to this distance, but we're just not really going to need to make use of that. It just doesn't really come up in the question if you read through. Okay, so the next question is to translate the given information as well as the desired information in terms of derivatives. So it tells us that the bottom of the ladder is moving away from the wall at a rate of 2 feet per minute. So that means that this distance here, as this ladder is moving, that distance is getting bigger. So specifically, we can say dA dt is equal to 2 feet per minute. And then what are we trying to find in this problem? Well, we want to know at what rate is the angle changing? And so we're trying to find d theta dt. So d theta dt is equal to question mark. Okay, so next step is to make an equation that relates the quantities in the problem. So specifically, we want to relate theta and A. So what kind of equations express a relationship between an angle and a distance in a right triangle, trigonometry, right? So we want to use a trigonometric function. So what distance or what information do we have in this right triangle? We have the opposite side from the angle and we have the hypotenuse. And so that means we want to use the sine function. So the equation we can write down is that sine of this angle theta is going to be equal to side A over 10. So that is our equation relating the two. So the next step is to take the derivative. And you could do it either way. I'm trying to think what is easier. Let's leave it as it is. If you wanted to, you could multiply both sides by 10 to kind of clear out the fraction. But I think you're just going to end up dividing by 10 at the end anyway. So let's just leave it as it is. Okay, so we're going to take the derivative of both sides. So we're going to take the derivative of sine of theta, and then we're going to take the derivative of A over 10. Okay. So what is the derivative of sine of theta going to be? Well, we know that in general that the outer derivative is going to be cosine. So we're going to have cosine of theta, and then we have to multiply that by d theta dt. Same way that we do for any derivative in these types of problems. And then on the right-hand side, well, and I don't know why I made this blue. Let me not do that. So on the other side, we have A over 10, and we can just pull that 1/10 out, right? Like you can rewrite A over 10 as 1/10 times A, and so 1/10 is just a constant. So we can just sweep it out and not worry about it when taking the derivative. And then what's the derivative of A? Well, the derivative of A would be 1, and then we multiply that with dA dt. So this is our equation. Okay, so last part is we're going to plug in things that we know, solve for what we don't know. And again, just like in the last problem, we'll see that there is a little bit more information that we need to kind of pull into this question. So if we look at what information we know that dA dt is 2, so we'll be good here. 1/10 is a number, so that's fine. We're looking for d theta dt, so that can stay in our equation. So that tells us that we do need to figure out what theta is, because otherwise we won't be able to solve for d theta dt. There will be too many unknowns. So how can we figure out what theta is? Well, let's look at the information that's given. So this asks us at what rate is the angle increasing when the bottom of the ladder is 5 feet from the wall. So when A is equal to 5. So we need to use that information to help us figure out what theta is going to be equal to. So here I'm just going to draw a picture that now represents, instead of being like a general situation, this is now a picture that's specifically of the time when this distance is 10 and this distance is 5. So in this precise moment we're looking at, where the ladder is a distance of 5 feet from the wall, it's going to be the case that sine of theta is equal to 5 over 10, which is 1/2. And so we can find theta by taking inverse sine of 1/2. So inverse sine of 1/2, which you can do looking at the unit circle, is going to be pi over 6. So now we know that we can, when we go to plug everything into our equation, we can plug in pi over 6 for theta. So now we can go back to this equation here and plug in what we do know and solve for what we don't know. So we have cosine of pi over 6 times d theta dt is equal to 1/10 times, and so dA dt was equal to 2, right? 2 feet per minute. So now we just need to solve this for d theta dt. So what is cosine of pi over 6? Well, again, if you look on the unit circle, you'll see that it's going to be square root of 3 over 2. So we have square root of 3 over 2 times d theta dt is equal to 2 over 10, which is the same as 1 over 5. And so to solve for d theta dt, we can multiply both sides by the reciprocal of 2 over 3, or sorry, of square root of 3 over 2. So that's going to be 2 over root 3. So if we multiply both sides by 2 over the square root of 3, that will get rid of the square root of 3 over 2 on the left-hand side. And on the right-hand side, it will give us 1/5 times 2 over the square root of 3, which is 2 over 5 root 3. And then if you wanted to, and I'm not too picky about this, but if you rationalize the denominator, so if you multiply by square root of 3 over square root of 3, that will give you 2 root 3 over 5 times 3, which is 15. So to answer our question, the angle that we were talking about is increasing at a rate of 2 root 3 over 15 radians per minute. Last example. So this one is definitely the trickiest just in terms of the kind of geometry and the picture that's going on in this case. So this one says a water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 6 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water is rising when the water is 4 feet deep. So again, let's start by drawing a picture. And again, this is going to be one where it's really going to be important to keep track of what is changing and what is not changing. So what is an inverted circular cone? It just means an upside down cone. So it's going to look kind of like an ice cream cone. So it has a base radius of 2 meters and height of 6 meters. So that means that the radius of this, this tank is 2 meters, and then the overall height of it is 6 meters. And then, well, like, that's not changing, right? This is not a question about a tank of water that is itself shrinking. So what is changing in this question? We have some water in this tank. So we want to also include that in our picture because that's really the part that we're going to be focusing on in this question. Okay, so the next part is asking to assign variables to the things that are changing in this question. So the height of the overall tank, that's not changing, right? The height is 6, it's equal to 6. The radius of this tank is not changing, that's equal to 2. So what is changing? Well, the height and the radius of the water in the tank. Right? So the water within the tank kind of makes its own like mini cone within the tank that's also a cone. So what is changing in this picture is the actual height just of the water and the radius of the water. So don't confuse that height and radius with the height and radius of the cone. It's just kind of like we have 2 cones in this question. So h is equal to the height of the water and r is equal to the radius of the water. Okay. So our next step is to look at what information is given and what information is desired and write that in terms of derivatives. So it says that water is being pumped in at 2 cubic meters per minute. So this actually brings up a variable that we have not yet introduced. And so this might bring us then to go back to step 2 and realize, oh wait, there's something else that we didn't account for here. So it says water is being pumped in at 2 cubic meters per minute. So when we're talking about cubic meters, that's like 3-dimensional, right? So what would that be describing the change of? That would be describing the change of volume. So we also want to add volume to our things that are changing. So volume meaning like the total space being taken up by that water. So I mentioned this in yesterday's video, but how can you tell that it's volume that's changing? I would really say it's the units. And also if it was, if they were trying to describe the change in height, they would say something like water's being pumped in so that the height is changing at blah, 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 blah. Anytime we're talking about like an amount of air or an amount of water or any other kind of fluid, we're talking about volume. So the first thing we can say here is that dV dt, the rate of change of the volume, is going to be equal to 2 cubic meters per minute. So what else is going on here? Well, it says find the rate at which the water is rising. So that's now talking about height. Right, that's like maybe it should say water level. I think that might make this a little bit clearer. But we're talking about the water rising, now we're talking about the height. And so dH dt is what we're trying to find in this question. Notice it doesn't tell us anything about the radius, or the rate of change of the radius. It doesn't ask us about the rate of change of the radius. It doesn't tell us anything about the rate of change of the radius. So there's no dr dt in this picture. So that's going to be kind of a hint to help us a little bit later on. Okay, so the next step is to write down an equation relating the quantities in step 2. So I wouldn't expect you to know this off the top of your head, but the equation that relates the volume and radius and height of a cone like this one is that the volume is going to be equal to 1/3 times pi times the radius squared times the height. So that's the formula for the volume of a cone. So before we get to the next step and take the derivative, I want to point something out. And it's basically what I just mentioned. We don't know anything about dr dt. It's not given. We also aren't trying to solve for dr dt. So that's kind of a problem. If we go in and we take the derivative of this equation, we're going to get a dr dt part, right? We're going to use the product rule on these two things, and part of that is going to be dr dt. And we just don't know anything about dr dt, and we're not trying to find dr dt. So it's going to leave us with too many unknowns to be able to actually solve. So what we're going to do instead is we're going to make use of some other information that was given to help us figure out how to get rid of r and express it instead in terms of h. So we're going to express r in terms of h so that the equation basically doesn't have too many unknowns. Okay, so let's go back to our picture here. So this is where this 2 and this 6 come in, right? We haven't really used that information that the radius and the height of the original cone are 2 and 6. So why is that important? It basically dictates the shape of the water that is within this cone, right? Like the proportion of the radius and the height to each other is going to be the same when you go down to lower and lower water levels, right? So even if I draw a water level that's down here, it still has that same ratio. The ratio of the height and the radius is the same. And really what that's coming from is similar triangles. So if you were to kind of take this, this cone picture and draw it instead as triangles instead of as a cone, so just like change it to being two-dimensional. So this was 6 meters, this here. Actually, let me do it as half of the cone. I think that will illustrate it a little bit more easily. And we only need half because we're talking about radius, right, which is half. So that would mean that this is 6 meters and this is 2 meters. And so the smaller amount of water forms a similar triangle with that top triangle. And so what that tells us is that whatever the radius and the height are, they're going to have the same ratio as they did in the original shape of the tank. So specifically, notice that the height is 3 times the radius. So that tells us that h is going to be equal to 3 times the radius, because 6 is 3 times 2. And so we're going to maintain that same ratio throughout the whole thing. So after we come up with that, then we're going to rewrite our equation. So now we can write our equation as v is equal to 1/3 times pi times 3, times 3, sorry, I got this backwards. H is equal to 3r, that's right. But that's actually not going to help us because we need to replace r with h. So we need to now solve this for r. Sorry about that, right? Because like if we're trying to get rid of r, we need to solve this for r. So that means that r is going to be equal to h over 3. So now we can go into our equation here, and instead of writing r, we're going to write h over 3. And then we can combine that with the h that we already have. So we're going to replace that r with h over 3, and then that has to also get squared, and then multiply that with h. So let's simplify this a little bit before we go and take the derivative. So we still have 1/3, we have pi, and then this becomes h squared. And then we have another h. And then the denominator of that fraction is 9. So one more step, let's really put this all together now. So the fractions can combine, and maybe let's throw the pi in there too. So we have pi over 27, and then we had a h squared times another h, so that's h cubed. So now we're ready for step 5, because now we have, now when we take the derivative, we're going to get only dv dt and dh dt, and we'll actually be able to solve. So what's the derivative of v? That would be 1 times dv dt. And then pi over 27 is just a number, so we can let that hang out front. And the derivative of h cubed, so that's going to start by giving us 3h squared. And then we have to multiply that by dh dt. So now we're ready to start plugging some stuff in. So dv dt we know is equal to 2. So we can put that in for dv dt. And then we have pi over 27 times 3, so that's actually going to simplify to pi over 9, right? Because 3 over 27 simplifies to 1/9. Then we know that h, so if we go back up to the problem, it says at what rate is the water rising when the water is 4 feet deep. So that tells us that we want to plug in 4 for h at the very end. So we're going to, so we already took care of that 3. Now we're going to put 4 squared. And then dh dt is what we're trying to find. So we'll leave that open here. Okay, almost done. So now we have 2 is equal to 16 pi over 9 times dH dt. And so to solve for dH dt, we can multiply both sides by the reciprocal of 16 pi over 9. So that would be 9 over 16 pi. So if we multiply both sides by 9 over 16 pi, we will get 18 over 16 pi is equal to dH dt. And then what does that simplify to? Well, they're both divisible by 2, so we get 9 over 8 pi is equal to dH dt. So we can finish this off by saying that the water level is rising at 9 over 8 pi, and the units were meters per minute. So that's it. So sorry, today's video is definitely on the longer side, but I just really wanted to make sure I went through all the details on these and really addressed anything that I expect you might have a question about. So definitely do try the examples on the worksheet for today. And yeah, I will see you all next week.